In this video, we're going to learn how to solve quadratic trig equations, but before we do that, we have to learn how to factor quadratic expressions with trig functions. So if we look at these first three examples here, our goal is to be able to factor each of these expressions. So when we factor, we want to make sure that, if we read the directions here, write each expression in factored form as an algebraic expression of a single trigonometric function. So that means we're going to try to get it. So like this first one's already in terms of sine, but the second and the third one have a couple different trig functions in there. We want to get it into a single trig function, and then we're going to factor. So for this first one, notice the form here. It's really a quantity squared plus 2 times that quantity plus 1. So you can kind of think about this almost as like y squared plus 2y plus 1. Um, I'm going to just keep this in terms of sine, though. I don't really want to convert it over to this variable, but if you need to convert it to another variable to kind of help you see how to factor it, that's fine. Just don't use the same variable that's already being used. So there's an x being used, so I definitely want to use a different variable other than x. So this is the trinomial that I'm trying to factor. So basically think about it as you're trying to add to 2, multiply to 1, and I have a sine squared x. So what's going to happen is we're going to break that down into sine x and sine x. And we're going to try to add to 2 but multiply to 1. So that's just going to be plus 1 and plus 1. So if you were to multiply this out, you should get back to the original. So that's it. If we look at the next example, now, like I said, we have sine, cosine squared together. So we want to make this have a single trig function first before we factor. So anytime we see cosine and sine together, if one of them is squared, you want to think about your Pythagorean identity. So what I'm going to do is I'm going to use sine squared plus cosine squared equals 1. So I'm going to use this identity. And if I get cosine squared by itself, that's equal to 1 minus sine squared of x. So what I'm going to do is instead of having cosine squared x, I'm going to replace it with 1 minus sine squared of x. That way, I'll be able to factor this. So let's go ahead and do that. So let me just replace first. So it's going to be sine x. Make sure you use parentheses when you're substituting in. So 1 minus sine squared of x minus 1. And now I can distribute this negative 1. So sine of x minus 1 plus sine squared x minus 1. Now we want to combine like terms, and we want to rearrange this in standard form. So I'm going to put my squared term first. So sine squared of x, then my non-squared term, so plus sine of x, and then we have a minus 2 when we combine those negative 1s. So now you want to factor this. So think about it as like a variable squared plus a variable minus 2. So breaking up sine squared x is going to be sine x and sine x. And then we're looking to add to 1 and multiply to negative 2. So we're going to have a positive and a negative. So a plus 2 and a minus 1 will multiply to negative 2 and then add to 1 because we have 1 sine x. So it's basically a coefficient of 1. So that's it. And again, if you multiplied those together, you would get back to this original. So number 3, again, I see a tan, a cosine, and a cosine squared. So right away, I'm thinking, how can I rewrite this so that I have all of the same trig functions? So I think, first of all, with tangent, I think about that as sine over cosine. That's how it's going to relate to cosine. So let's replace that. So we have sine x over cosine x times cosine x. And then this minus 2 times cosine squared. Well, right away, I know that these are going to cancel out the cosines. So now I actually have sine and cosine again. So since I have a cosine squared, I'm going to go back and I'm going to use the same thing over on what I used on problem 2. I'm not going to rewrite this since I have it right next to it. And you don't necessarily have to show this every time that you're plugging in, especially when you get to these more complex equations. You're going to start using it a lot. I know I wrote it when we first started, but from really here on out, once you see a cosine squared of x or a sine squared of x, you can use this identity. So I'm going to go ahead and I'm going to just plug right in the 1 minus sine squared of x. And then from there, now I can simplify this. And again, I knew to do the sine squared and not leave it as cosine squared because my cosines canceled. So now I have 3 times sine of x minus, I'm going to distribute this out, so minus 2 plus 2 sine squared of x. Get this in standard form. So 2 sine squared of x plus 3 sine of x minus 2. And now I have to factor this. So off to the side here, if you want to think about this, in terms of another variable, so, for if you need help with this to factor, what you can use is you can use the grid to factor. So you can think of this as 2y squared plus 3y minus 2, basically letting sine x equal y. That's what I did. And then I can use the grid if I need to. So in order to use the grid, first term, first box, last term, last box, we're looking for numbers that are going to add to 3, but then multiply to negative 4. So we're going to have 4y and minus 1y will get us to multiplying to negative 4, but then adding to 3. GCF out of the top row, so I have 2y. Now look at 2y times what gives me 2y squared? That's a y. 2y plus 2 is going to give me 4y, or I should say 2y times positive 2 is going to give me 4y. Y times negative 1 is going to give me negative y. 2 times negative 1 gives me negative 2. Here's my factors right here. So when I go back up top here, I can write that as 2 sine x minus 1. So basically just plugging in sine x for y, and sine of x plus 2. Now, again, you don't have to show this grid. This is just one of the factoring techniques if you need help with it, especially when the leading coefficient isn't 1. You might feel like you want to do the grid, or maybe you want to do like factor by regrouping. It doesn't really matter. Guess and check. I mean, this one would have been easy enough to do with guess and check because 2 only has one set of factors, 2 and 1. But it's up to you. So it's really your call on how you want to go about getting to where you need to factor. So now that we can do that, now we can solve these higher level trig equations, the quadratic trig equations. So we're going to start off the same way that we solved for linear trig equations, or I should say first degree, not linear, but first degree trig equations. So what we're going to do now is we're going to first focus on isolating the trig function. So when I go to look at this, I'm solving these in degrees from 0 to 360. And for number 4, I want to think about, okay, well, how can I solve this equation? So if it's a first degree, you isolate your trig function. In this situation, in order to isolate my trig function, I'm going to have to factor. I'm going to have to be able to think about this as kind of like a quadratic. How do you solve a quadratic equation? Look to see if you can factor. So in this situation, I can factor out a sine of theta out of both. So I'm going to go ahead, factor out sine of theta. So I have 2 sine of theta minus 1. And now what happens is I can split this since it's a product equal to 0 and set each piece equal to 0. And now I can think about these as my first degree trig equation. So now I'm going to isolate my trig function. So this one's already good to go. Over here, this is going to end up being 2 sine of theta equals 1, sine of theta equals 1/2. And now I want to find my reference angles. So when we have 0, sine of theta equals 0, you want to think about your unit circle and when does the y value equal 0. So there's two places where the y value equals 0. It's going to be when it's 1 comma 0 and negative 1 comma 0. So we're in degrees, so this is going to be at 0 degrees and at 180 degrees. Notice that we're not including 360, so I don't want to include that. So for this left-hand side, I have answers of 0 degrees and 180 degrees. So those are two of my answers. And then on this right-hand side, well, now I'm looking at when does sine of theta equal 1/2. So this is going to be one of my special right triangles because it's the opposite over the hypotenuse. It's going to be a 30, 60, 90 triangle. Where sine is positive is in the first two quadrants. So we're looking at those reference triangles. So opposite over hypotenuse is equal to 1. So we're looking at a 30-degree reference angle here. So my reference angle is 30. I'm going to actually write this smaller. So now my first theta here is going to be 30. And over in the second quadrant, well, that's 180 minus 30, so that's going to be 150. So for this equation, we had 4 total possibilities. Number 5, same process. So again, you want to try to isolate your trig function, but before you do that, you have to think about how do you algebraically solve this? How do you algebraically solve a rational function? So in this case, we have fractions. We have a fraction equal to a fraction. So your first step in trying to get your cosine by itself is actually to cross multiply. So we're going to have to cross multiply first. So we end up with distributing this cosine through. So it's going to be cosine squared theta minus cosine. And remember, when you multiply a cosine by a cosine, the squared actually touches the cosine because that's indicating that it's cosine theta quantity squared. It's the whole thing squared. And then on the other side, we get equals 2. So now we want to think about algebraically, well, what would be our next step? Well, now we have a quadratic. If we can get this equal to 0 and then factor, then we'll be able to set each individual piece equal to 0. So that's going to be my process. So now I'm going to bring that 2 over to the other side. Now I want to think about factoring this. So we're going to have a cosine theta and a cosine theta. And if we factor, we're looking at adding to -1, multiplying to -2. So -2 plus 1 would do that. And then we can split this, so each piece equal to 0, since it's a product equal to 0. And now we have our linear or our first degree situation here. So now we can isolate cosine. So cosine theta equals 2 and cosine theta equals -1. So cosine theta equals 2. This can never happen. And if you think about it, I think about the graph is probably the easiest way to think about this. When you're looking at your cosine curve, it starts up at 1 and it goes down to -1, back up to 1, and then it just continues. It will never go up to 2 unless we have like a shift change or the amplitude's different. But if it's just cosine theta by itself, it can never equal 2. So this can never happen. So cosine will never be greater than 1. So never greater than 1. So basically that just tells us there's no solution on the left-hand side. That's really what this is telling us. So now we only need to focus on the right-hand side here. So now we think about this one. And since it's a -1, I'm looking for an x value of -1, which is going to be on my unit circle, and it's going to be at 180 degrees. And that's the only place, so theta is equal to 180 degrees. That's the only solution here. So notice the variation between these were both quadratic, but this one only has one solution, and this one over here, number 4, had 4 solutions. So you really have to consider all possibilities, and really it's a case-by-case scenario. So each problem is going to be a little bit different. So let's keep going. Let's keep trying more of these just so that you become comfortable with it. So number 6, we have cosine squared and a sine. So that tells me right away I want to replace my cosine squared using the Pythagorean identity. I don't want to try to replace sine because there's not a way for me to do that. So I'm going to use my identity. I'm going to just write it as cosine squared theta because it would normally be plus sine squared equals 1. So I'm just going to go ahead and solve it. So it's going to be 1 minus sine squared. Like I said, you don't necessarily have to show this every time. Once you become comfortable with it, just go ahead and use it. So I'm going to replace that. So it's going to become 2 times 1 minus sine squared minus sine of theta. I'm going to go ahead and just bring this 1 over in this step. Minus 1 equals 0. So now I can go ahead and combine like terms. So I'm going to distribute my 2. So 2 minus 2 sine squared of theta minus sine of theta minus 1 equals 0. Get our like terms, get this in standard form. So I have plus 1. And now I don't want to have a negative leading coefficient for factoring purposes, so I'm going to divide everything by -1. So this is just going to swap all the signs. And now I need to factor. So again, if you prefer, use the grid for factoring. You don't have to, but if you prefer it, you can use the grid. You can also just kind of use guess and check here. So think about you need to be able to multiply to 2 sine squared of theta, the first terms. Well, that means one of them is going to have to be 2 sine of theta. The other one's going to have to be sine of theta. And now we need to have a combination so that we end up adding to sine of theta, but then multiplying to a -1. So if we're multiplying to a -1 here, so I'm just kind of using guess and check, that tells me that I'm going to have a +1 and a -1 to be able to multiply to a 1. Well, in order to get sine squared, or not sine, sine of theta, when I FOIL this out or double distribute, I would have to make sure that the 2 sine would have to be a positive. So 1 times 2 sine would give me a positive 2 sine of theta. And then minus sine of theta would give me sine of theta. So that would be my factors. Like I said, you could totally use the grid. If you were going to use the grid, you would want to use 2y squared plus y minus 1 to factor. And then you would get the same factor. So it's up to you how you want to do it. I'm going to skip showing the grid just for the sake of time, but if you'd like to do it, go for it. So here are my factors. So then now I can split it. So 2 sine of theta minus 1 equals 0. Sine of theta plus 1 equals 0. So 2 sine of theta equals 1. Sine of theta equals -1. This is going to be sine of theta equals 1/2. So I've isolated my first degree trig functions. So now I'm going to solve them like normal. So I have my 4 quadrants. All students take calculus. It's going to be positive for sine. So I'm looking at first and second quadrants. Hypotenuse is 2. Opposite is 1. And I'm looking at my 30, 60, 90 right triangles. So these are going to be reference angles of 30 because they're across from the 1. And again, you could label the rest of the triangles. You don't really have to. You really just need to get the reference angle. So I know that the reference angle is 30. So in the first quadrant, we're going to be at 30 degrees. In the second quadrant, 180 minus 30 is going to give me 150. So there's my 2 solutions from from the left-hand side. From the right-hand side, we're looking at when does sine equal -1. So when is the y value -1? And that's going to be down here at 270 degrees on our unit circle. We're going to have a y value of -1. So that theta ends up giving us 270. So now I have 3 solutions for this equation. Looking at the next problem here, we have just tan squared. So since it's just tan squared and the rest are numbers, we can actually isolate the tan squared and then use the square root method to solving. We don't have to factor this one because of it only having a tan squared in numbers. You could do difference of two perfect squares, even though the 3 isn't a perfect square, you could just write it as root 3 and root 3. But I think it's easier for this one to just get your squared term by itself. So I'm going to isolate the squared term. So divide both sides by 3. So I get tan squared of theta equals 1/3. We're going to square root both sides. Remember, when you square root a variable that was squared, you have to indicate plus or minus. And when you square root 1, you get 1. When you square root 3, you're going to get root 3. So it's plus or minus root 3. So think about this on your 4 quadrants. Well, all students take calculus. In this picture, we have our 2 positives, but we also want to include our negatives. Where is tangent negative? So we really have all 4 quadrants for this one. So go ahead and draw your triangles in all 4 quadrants. And they should all be congruent. I know mine doesn't look that way, but that's okay. We're really just looking for the numbers here. So we're looking at the opposite over the adjacent. I purposely did not rationalize this because I recognize 1 and root 3 as coming from my 30, 60, 90 triangle. So I purposely didn't want to rationalize it. So opposite is going to be 1, adjacent is going to be root 3. Same thing with all of these. So you can see, you can kind of fill in. So the adjacent's going to be root 3. So if it's going left, it's going to be negative. The opposite's up or positive. Opposite going down is negative. My hypotenuse is going to be 2. Not that we really need to label it. All we really care about is what is the reference angle. Well, the reference angle is across from the 1, so that's going to be 30. So if I'm not going to try to, I feel like I don't have enough space to label my reference angle, so I'm just labeling it here instead. So my first quadrant, I get 30 degrees with my reference angle of 30. Second quadrant, 180 minus the 30 is going to be 150. Third quadrant, 180, so 180 plus the 30, we're going to have 210. And then this fourth quadrant here, this angle, so all the way around, so it's going to be 360 minus the 30, so 330. So there are my 4 solutions for this problem. So let's try a couple more on this next page here. So again, we're really kind of putting our algebra, quadratic equations with this trig stuff. So we're getting into some pretty complex equations here. So for these 4, we're going to solve these and leave our answers in radians. So same process, it's just when we're all done, we're going to make sure our answers are in radians. So when I look at this problem, I see that I have cotan and I have cosine. So first of all, I'm going to get this, well, when I look at this, I see cotan and cosine, and I think, okay, well, the only relationship is really cotangent can be written as cosine over sine, but then I'm going to have a sine and a cosine squared, and then I guess we could change the cosine squared in terms of sine, but I'm not sure if that would actually all end up working out. I didn't do it that way, but it could. The way that I thought to do this is, why don't we bring this 2 cotan over to the other side? Because then I can factor out a cotan. So look at this one for a second. It's a little bit different. So we have cotan x cosine squared of x minus 2 cotan of x equals 0. So if I bring that over, now what I can do is I can factor out a cotan. So I'm left with cosine squared of x minus 2 equals 0. And this is unique because normally I say you want to get the same trig function before you start solving. But this one, since we were able to factor it and have cotan on one side and cosine on the other side of the product between the two, this is going to allow me to split this and say cotan of x equals 0 and cosine squared of x minus 2 equals 0. And it doesn't really matter that I have two different trig functions because I'm going to solve these now individually as two separate trig equations. So this is a unique situation. Normally you want to try to get it all in terms of the same trig function, but in this case, I don't know if it would have been possible for me to get it in terms of the same trig function, maybe, but I'm not sure if it would be. So this is definitely the strategy that I think is the quickest way for sure. So just kind of keep that in mind, that if you can factor out a common trig function, then do that, because then that'll allow you to solve this a little bit quicker. So now when I think about cotan of x equals 0, remember, this would be the same thing. So this is 0 over 1. So this is really the same thing as me saying, well, when is tangent undefined? So basically, when does, remember, tangent's like saying sine over cosine. So since we're looking at 0 and undefined, this is really coming from our quadrant angles. So think about, when does sine over cosine become undefined? So sine over cosine, when is that undefined? Or when does cosine divided by sine equal 0? However you want to think about it. In either situation, what you really need to know is, when does cosine equal 0? So if tangent is equal to y over x, you want to know, when is x equal to 0. So that's going to be in two places on our unit circle. That's going to be at 0, comma 1 and 0, comma negative 1. So that's where you would be doing 1 divided by 0, negative 1 divided by 0 to solve this. So that's going to be at pi over 2 and 3 pi over 2 if we're in radians. So that means x is going to be pi over 2 and 3 pi over 2. So you could solve that one either way. You could look at cotan. I usually like to make my reciprocals. I usually use the reciprocals and then just reciprocate that. I don't know if that's a word, but take the reciprocal of this. So then for the next one here, cosine, I'm going to go ahead and isolate my squared term. And I'm going to square root both sides. So cosine of x equals plus or minus root 2. So for this, root 2 is bigger than 1. So this isn't going to happen. You're never going to have, remember when we talked about this, cosine of x has to be between or equal to 1 and negative 1. So it won't be, so this is never going to happen, so you won't get a solution from that side. So basically these are your only two solutions. So looking on to the next one here, so we have some, it looks like, it would be good to go to factor if this was sine and sine. So we have sine squared of x, but now we have a cosine. So this tells me I need to get this sine squared of x. I need to get that in terms of cosine so that I can actually factor. So what I'm going to do is I'm going to use my Pythagorean identity here. So I'm going to use the fact that sine squared of x is equal to 1 minus cosine squared of x. Remember, that's just coming from sine squared of x plus cosine squared of x equals 1. So I'm going to go ahead and just rewrite this. So 2 times 1 minus cosine squared of x. And for this one, I have to get it in terms of all of cosine first, because there's no way for me to factor this without doing everything in terms of cosine. So that's why I'm doing it, versus the last one, I could factor something out. So go ahead and distribute. And then combine like terms. So 2 cosine x plus 3 cosine x is going to give me minus 1. And now again, I want to divide everything by negative 1 because I never want to try to factor with a negative leading coefficient. So essentially, I'm just flipping my signs. This is one where you might want to use the grid since your leading coefficient's not equal to 1. But I think for this, it's easy enough to factor using guess and check because my leading coefficient is 2. So that means I'm going to have 2 cosine x and 1 cosine x to multiply and get that leading coefficient. We're looking to multiply to 1. So again, that tells me that I'm going to have a 1 and a 1. And since I'm multiplying to a positive 1, I have to have the same sign. In order to get -3 when we add these, so if I have -2 cosine x and negative cosine x, that's going to actually give me my -3. So that's going to allow me to have a negative, and that would work for factoring. Again, you could use the grid, you could use another factoring technique if needed. So I'm going to go ahead and just finish solving these. So I have set each piece equal to 0. So this is just going to end up being, I'm going to kind of combine a couple steps here. So this is going to end up being, we'll bring the 1 over, so it's going to be cosine x equals 1/2 when we solve that. So you bring the 1 over, then divide by 2. This is just going to be cosine equals 1. And then for this, cosine of x equals 1/2, you're looking at where is cosine positive. So first and fourth quadrant. So adjacent over hypotenuse. So we're looking at our 30, 60, 90 right triangle. So we're looking at a 60-degree angle this time, or a reference angle of pi over 3 radians. So my first quadrant is going to just be pi over 3. And then for my fourth quadrant, we'll think about this as this is pi, this is 2 pi. We put that with a denominator of 3. Well, this is the same thing as saying 3 pi over 3. This is 6 pi over 3. So 1 less pi over 3. So if this is pi over 3, you want 1 less than 6 pi over 3. That's going to be 5 pi over 3. Oops, I didn't mean to write that there. That's supposed to be up here. So there's your left-hand side. And then for your right-hand side, since you have 1, we're looking at our unit circle. We're looking at our quadrant angles. So where does x equal 1? That's going to be right here at 0 degrees or 0 radians. So this is just going to be x equals 0. I don't include 2 pi because my up in the directions it tells us to go up to 2 pi, not including 2 pi. So that's it. 2 more. If you feel like you have the hang of this, feel free to stop the video. I know we're getting a very long video here, so feel free to stop the video and try these on your own. I'm going to keep going through them just because I know they're a little bit different, but feel free to stop the video at any point once you feel like you have the hang of it. So when I look at number 9, this one as is, I can't really do anything because I can't rewrite cosine or sine and make them each other. So like I can't take cosine and make it sine. I can't take sine and make it cosine unless they're squared. So because if I square each side, this would create some cosine squareds and sine squareds. That's going to allow me to use the Pythagorean identity. So that's the whole idea here of why I'm going to square each side. And you can do that as long as whatever you do to one side, you do it to the other. That's totally fine. So what I'm going to do is I'm going to square this. So I end up with, let me just write it out since we're dealing with cosine and not just regular variables here. So cosine x plus cosine x, or cosine x plus 1, I think I said that totally wrong. Cosine x plus 1 times cosine x plus 1 is equal to sine squared of x. So now I'm going to FOIL this out or double distribute so I get cosine squared x. This is going to be a plus cosine x times a cosine x. So I'm going to have 2 of those. So 2 cosine x. If you need to write that out, you can. And then plus 1 equals sine squared x. So now I kind of know which one needs to go. I know that the sine squared x is what needs to go. I need to replace this in terms of cosine because I have cosine and cosine here. So what I'm going to do is I'm going to rewrite this as cosine x plus 2 cosine x plus 1 equals, so instead of sine x squared, this is going to be 1 minus cosine squared of x. So again, I just used that Pythagorean identity. I didn't show it again because we've used it so much, but that's exactly what I did. So now I can regroup this, combine like terms. So I'm going to bring this cosine squared x, so I end up with 2 cosine squared x plus 2 cosine x. subtract the 1, so now I just have equals 0. So this is nice because for factoring it's a little bit easier because I can just take out a 2 cosine x from both. So take out a 2 cosine x, I get cosine x plus 1 equals 0. Now I can split it, so 2 cosine x equals 0, cosine x plus 1 equals 0. And then from here, I have divide by 2, so I have cosine x equals 0, and then this one's cosine x equals negative 1. So this looks like unit circle for both of these. So when does x equal 0? Well, x equals 0 at 2 points, at 0, comma 1, and at 0, comma negative 1. So we're in terms of radians, so this is pi over 2 and 3 pi over 2. So x equals pi over 2 and 3 pi over 2. And then for this side, when does x equal negative 1? Well, that's only in one place. That's at pi, so we get x equals pi. You can list all of these answers together too, just so you know it doesn't matter if you list them separate or not. So that's it for that one. So then the last one here, we have tan x and tan squared of x. So we're all in terms of tan, so I'm going to leave it in terms of tan. I'm thinking let's get this equal to 0 so we can factor. So I'm going to bring the tan x over to this side. So I'm going to have tan squared of x minus tan of x equals 0. And now I can factor out a tan x. So I have tan x minus 1 equals 0. Set each piece equal to 0. Oops, I shouldn't have drawn that line. Equals 0. And then tan x minus 1 equals 0. So we're solving for when does tan of x equal 0 and when does tan of x equal 1. So tan of x equals 0. I always think about this as sine over cosine. So sine is y and cosine is x. So we want y divided by x to equal 0. So that means you got to have a 0 in the numerator. So that means we're looking for when does y equal 0. So when does y equal 0? Well, that's going to be 1 comma 0 and negative 1 comma 0. So that's going to be at 0 and pi. So 0 divided by 1 is 0. 0 divided by negative 1 is 0. That's why these work, because it's sine divided by cosine. So 0 and pi radians. And then for the last piece here, tan of x equals 1. Well, now I want to think about this as opposite over adjacent equaling 1. 0 and undefined for tan are the times when you're going to be looking at your quadrant angles or your unit circle and the points on the unit circle. So when I'm looking at 1, that means I'm looking at an isosceles triangle because opposite over adjacent cancel out and end up equaling 1. So that's how I know it's isosceles. So where is it positive? First and third. So opposite over adjacent, opposite over adjacent. So we're looking at our 45. So my reference angle here is going to be pi over 4 radians. So I guess I can fit it in there. Pi over 4, this is root 2, not that that really matters. Pi over 4, so I'm looking at my first angle in the first quadrant, just pi over 4 radians. And then over here, this is going to be, remember, think about this as pi and 2 pi, but in terms of a denominator of 4, well, this would have to be 4 pi over 4, and this would have to be 8 pi over 4. So if you have one more pi over 4 past 4 pi over 4, you're at 5 pi over 4. And that would be your angle, your other solution. So that's it. I know this is a long video, so I want to end it. But just remember all of your algebra strategies here, all of your factoring first to get down to those first degree trig equations, and then it's just using the strategies from the previous video. So go ahead, try the homework problems, and that's it.